Good afternoon. Today we're going to sort of backtrack just a little bit into section 1.7, and then we will get back with the composition of functions. And for what we have at the moment, okay, and this is going to sort of transition over to items which will be in chapter 2, which is going to be in the third test material. And we have what are referred to as odd and even functions. And for what we have in the case of odd and even functions, and we have regarding some of the characteristics. Okay, now in the case of odd and even functions, okay, now we have for odd functions. Okay, now for an odd function, okay, that is going to be a function that's going to have symmetry with respect to, or I could also say it's going to be a function that is reflected about the origin. Okay. And in the case of the xy coordinate system case, you have the origin will be where both x and y are 0. And an odd function is going to be defined by the relation okay, where in this particular case, okay, we want to have that f. If you take the opposite sign of x, okay, so you have f of negative x is going to be equal to the negative of f of x. And in the case of odd functions, what you're going to have here, in effect, is that opposite sign inputs create opposite sign outputs. And I'll just stress this. Okay, so we have, again, so you have opposite sign inputs. We're going to create opposite sign outputs. Okay, and now just looking at what we have, let's say, as a visual case of an odd function. Okay, an example of an odd function could be whereupon we have that f of x is equal to x to the third plus 2x. Okay, and we'll get into some of the finer details, okay, about this relation f of negative x is equal to the negative of f of x. But just looking at what we have for this particular function, okay, just looking at the characteristics Okay, we have reflection about the origin, and again, opposite sign inputs will create opposite sign outputs. And for what we have from a visual perspective, okay, so we have for f of x is equal to x cubed plus 2x. If you see, you have the origin where both the x-axis and the y-axis are going to meet, okay, and you're going to have for f of x is equal to x cubed plus 2x. Now, this function crosses the origin, and if you notice for the halves, okay, in the first quadrant, or where both x and y are positive, okay, you have the curve to be going up and to the right, and we have over in the third quadrant, and that's where both x and y are negative, okay, to the same degree, just as the function is going up and to the right, we have to the same level, we have going down and to the left, okay, with respect to the origin. And again, we have reflection about the origin, so you can think of like these halves mirroring each other about the origin, you know, up to the right, down to the left, to the same intensity level. And if you notice, we have opposite sign inputs create opposite sign outputs. So you got the origin, and for x at negative and positive 1, when x is negative 1, y is at negative 3. When x is 1, y is positive 3. And when x is negative 2, the output is negative 12. And when x is 2, okay, we have that y comes out to positive 12. Okay, and you're going to continue this pattern. If you have like negative and positive 3, your outputs are going to be, again, additive inverses. Okay, and so this is what we have in the case of an odd function. Now, for what we have in the case of the other type of function, and this is what we're going to have in the case of even functions. And we have for an even function, okay, now an even function, you're going to have reflection, but it's going to be with respect to a different reference. And instead of being reflected about the origin, it's going to be reflected about the y-axis. And in terms of relations, and this time we're going to have f of negative x is equal to f of x. Okay, and both of these functions, okay, we have in the general case, those are positive. And for what we're going to have here, okay, notice you have f of negative x and f of x. They are said to be equal to each other. And what this is going to translate to is that for an even function, okay, and we have opposite sign inputs. Are going to create, instead of opposite sign outputs, you're going to have identical outputs instead. Okay, so we have opposite sign inputs create identical outputs. And we can take, like in the case of the example of an even function, we say we have f of x is equal to x squared minus 2. And for what we have here, okay, so you have f of x is equal to x squared minus 2. Now the type of graph that this is going to be is a parabola. Okay, and again, f of x, another way of saying y, is equal to x squared minus 2. And this time around, okay, if you notice, we have symmetry, not with respect to the origin, okay, but you have both halves to be mirroring each other about the vertical or y-axis. Okay, and again we have for the left and the right halves. Okay, so you have at x is equal to 0. Okay, you have 0, negative 2, and this is going to be like the minimum. But for the opposite sign inputs, you have like negative and positive 1. Notice the outputs we have with the y values, we have negative 1, and see that should also be 1, negative 1. Now, so you have negative 2, 2, and positive 2, 2, negative 3, 7, positive 3, 7. And again, you have, for even functions, opposite sign inputs lead to identical outputs. Okay, so additive inverse x values lead to the same y value, whereas in the case of odd functions, again, opposite sign x values lead to additive inverse y values. Okay. And for what we have in the case of odd and even functions, okay, say if you want to look at identifying the characteristics of odd and even functions without having to graph, and we'll start out like in terms of what we have for f of x. We'll see we have f of x is equal to x cubed. Okay, and to see how f of x here is going to relate to f of negative x. Okay, so again we have f of x is equal to x cubed. Now, if I put in place of x, I have negative x. Again, we have with this function, have f of the input is equal to the cube of the input. Now, if the input is negative x, so you have the cube of negative x, and so this is going to be negative x cubed. And what I'll do here, you got f of x is equal to, again, you have x cubed. Now I'll just duplicate this and just sort of line up how both the inputs and the outputs will relate. Okay, and so for what we have in the case of x and negative x, okay, if you notice, okay, we'll go through sampling, okay, where we have opposite sign inputs throughout, and to see how the outputs are going to compare. Okay, so we've got opposite sign inputs. Now for the outputs, okay, for f of x, you had the output at positive x cubed, whereas for f of negative x, you have opposite sign. Okay, and for what we have here, if you have opposite sign inputs leading to opposite sign outputs, okay, what is going to happen here is that for this cubic function, okay, this winds up becoming odd. Now let's say that if I have that f of x is equal to x to the fourth plus 3x squared. Okay, so just looking at what we have for f of x, okay, you see how the opposite sign inputs will lead to their respective outputs. So for the input at x, okay, so you have x to the fourth plus 3x squared. And if I take f of negative x, okay, so you have, with a couple of x terms, I have a couple of things happening. So I'm taking the fourth order of negative x, and I have plus 3 times the square of negative x. Anyway, for even powers of terms that are negative bases, okay, you're going to have a positive term. In this case, a negative x to the fourth, that becomes x to the fourth. Now the square of negative x, think like negative x times negative x, is going to be a positive x squared. And so for what we have in this case, right, so you have, starting out with opposite sign inputs. And if you notice in the outputs, okay, we have x to the fourth and 3x squared from f of x, and you have likewise x to the fourth and 3x squared and unanimously, okay, you have the output terms to be identical. Okay, so if opposite sign inputs lead to only the same output, okay, what's going to happen here is that for this function, this is going to be a case of an even. So f of x equals x to the fourth plus 3x squared. Okay, this will come out as an even function. Now let's say that if I have f of x is equal to 3x to the fifth okay, I'll say I have 3x to the fifth plus 7x to the fourth minus 6. Okay, so again, working with opposite sign inputs. Okay, so we already have f of x provided, and looking at how the output is going to appear for f of negative x. Okay, so we have 3 times, okay, the fifth order of negative x. We have plus 7 times the fourth order of negative x. And again, we have followed by the subtraction of 6. Now for negative terms raised to odd powers, again, we have a negative. Okay, so we have 3 times the negative of x to the fifth, so this will be minus 3x to the fifth. Negative x to the fourth, that's going to be a positive x to the fourth, multiplied by 7. So yeah, plus 7x to the fourth and minus 6. Okay, that is already locked in as the constant. And for what we have in this particular regard, okay, so we got for the first output terms, we got 3x to the fifth and negative 3x to the fifth. Okay, these are opposite. And had the rest of the terms been opposite sign, we would have had an odd function. But as it turns out, we have 7x to the fourth is positive for both f of x and f of negative x. And we have negative 6 for both f of x and f of negative x. And if you notice, we don't have unanimously the same throughout, and you don't have unanimously opposite throughout. So when there's a bit of static, like opposite for some and same for others in the output terms, what happens here is if you don't have it like the same throughout leading to an even function, or just opposite only leading to an odd function, if you have a blend, what happens here is that we come out to where we have this function is neither odd nor even. So like the graph would not have symmetry with respect to the origin, since it is not odd, nor would it have symmetry with respect to the y-axis, since it's not an even function. Okay, so as in this case, this is where we have one that is not odd or even. And let's say that if we have, and we'll create a tiebreaker in this in case you got one odd, one even, one neither. And for this last case, to see which one is going to come out ahead. Okay, say we have f of x is equal to x to the fourth plus 3x squared minus 1. Okay, so we got for f of negative x, okay, so you have opposite sign inputs. And if you can see the result intuitively, that's fine. We're just looking at it breaking down incrementally. Okay, so we have for, again, negative terms to an even power will become positive. So we have a positive x to the fourth. And we have the square of negative x, it will be positive x squared multiplied by 3. So we have plus 3x squared, and we have minus 1. Okay, so we start out with opposite sign inputs. If you notice, we have x to the fourth and x to the fourth. And we have positive 3x squared and a positive 3x squared. And both f of x and f of negative x have negative 1. And we have all of these are going to be the same. And if we have the output terms to be unanimously identical, in spite of the opposite sign input, it turns out that this function will be even. All right, so these are just quick cases, okay, of what we have with odd functions and even functions, as well as the characteristics that are associated. All right, now kind of going back to what we have with the composition of functions, and we have from section 1.8, okay, and we have okay, say for number 47, okay, we have in this particular problem set, okay, we have three functions, f of x, g of x, and h of x. And f of x we have as the cubic function, whereupon we have x cubed minus 4x. And for g of x, okay, we have this as a radical function, where we have this to be equal to the square root of 2x. And h of x is a linear function, where this is defined by the binomial 2x plus 3. Okay, and looking at evaluating the functions, okay, so here we have a specified input where x is at 8, and just sort of laying the groundwork for what we have in number 47. Okay, so you have f of g of 8, and there's kind of reintroduce this in the case of the formal composition notation. So again, you have f composed with g of 8. Again, so you have f composed with g of 8. So this will lead to f of g of 8. Okay. All right, so g of 8 is going to be the input portion, and the output will be in reference to f of x. Okay, and just taking what we have here. So in terms of what I'm going to do with g of 8, I'm going to operate in line with f of the input. And by definition, f of the input is equal to the cube of the input minus 4 times the input. Now that the input is g of 8, now we have with the notation, okay, there's a little bit of a crowding effect with the parentheses, but again, you're looking at the cube of g of 8 minus 4 times g of 8. Okay, so this is what I have at the substitution stage. Okay, but now if I specify, okay, just what is the value of g of 8? Well, referencing g of x is equal to the square root of 2x. Okay, so if x is at 8, we're going to have for g of 8, okay, so you have the square root of 2 times 8. We have 2 times 8 is 16, and the square root of 16 is only 4. Okay, so g of 8 is equal to 4. And with that value specified, okay, so for the cube of g of 8, okay, so you have the cube of 4. We have minus 4 times g of 8. Okay, so looking at minus 4 times 4. And evaluating, okay, so you have 4 cubed. Okay, that is going to be at 64. Negative 4 times 4. Okay, there'll be negative 16. And narrowing it down. Okay, so you have 64 minus 16. This comes out to 48. Okay, now for the next item, okay, we have for number 48. Okay, now we have h composed with g of 2. Okay, so we got h of g of 2. Again, so we're going to operate along the lines of h of x. And from the trio, okay, so h of x is the linear function we have defined by 2 times the input, followed by the addition of 3. And for h of g of 2, okay, so we're looking at 2 times g of 2, followed by the addition of 3. Okay, and again, so going back to g, okay, and if I specify the value of g of 2, so again, g of x is equal to the square root of 2 times x, and with x at 2, okay, so I have the square root of 2 times 2. 2 times 2 is 4, square root of 4 comes out to 2. And inputting 2 for g of 2. Okay, so we have 2 times 2 is 4, and we have that 4 plus 3 is equal to 7. And that'll be the final answer in this problem. All right, now for what we have in the case of number 49, okay, now we have h of f of 1. And just reintroducing this again with composition notation. Okay, so I have h composed with f of 1. Okay, so I have f of 1. And again, we're operating again along the lines whereupon the output is in line with h of x. Okay, so again, h of the input is equal to 2 times the input plus 3. Okay, and so we have on the parallel note, okay, so we have with f of 1 in place of x, so we're looking at 2 times f of 1 followed by the addition of 3. Okay, and again, we have with our function f, again, have f of the input is equal to the cube of the input minus 4 times the input. So in this case, we have f of 1. So we have 1 cubed minus 4 times 1. 1 cubed is 1. We have minus 4. And 1 minus 4 will be at negative 3. Okay, and so we have for 2 times f of 1, okay, this is going to become 2 times negative 3. Followed by the addition of 3. 2 times negative 3 is negative 6. And we have negative 6 plus 3 at negative 3. All right. Now, for what we have in continuing with the compositions at specified inputs for x, okay, now we have for number 50, okay, so we're looking at g composed with f of 3. So you have in this particular case, right, so you have g of f of 3 and operating in line with, okay, where we have the output in terms of g of x. So again, we have by definition g of the input is equal to the square root of 2 times the input. And now with the input at f of 3, okay, so we're looking at the square root of 2 times f of 3, okay, and looking at evaluating f of 3, okay, so for f of the input, we got the cube of the input with the input at 3 minus 4 times the input. Okay, so we have 3 cubed. Okay, that is going to be at 27. Negative 4 times 3. Okay, so we have it minus 12. And 27 minus 12 comes out to 15. So here we have the square root of 2 times 15 and so for the outcome here, this is going to end up as the square root of 30. Okay, and now 30, it is a fairly large even number, and perhaps surprisingly, okay, the highest perfect square divisible into 30 is only 1. Okay, so the square root of 30, okay, that is already in reduced radical terms. All right, now, and this is probably going to be surprising and perhaps even more so for what we have for number 52. I think we'll have a radical, and this one is not going to be quite so. Actually, it might be one that's farther on down, but we'll look and see what we have here. Okay, so you have f composed with h of negative 1. Okay, and again, operating along the lines of f of x. Again, f the input. You got the cube of the input minus 4 times the input. Okay, so we have for the cube of the input, now we have the input with h of negative 1. Okay, and looking at specifying, okay, just what h of negative 1 is. Okay, and again, we have our h of x. Okay, that is at 2x plus 3. So for h of negative 1, we will have 2 times negative 1 plus 3. 2 times negative 1 is negative 2. And negative 2 plus 3. Okay, so that will come out to 1. Okay, so you got 1 cubed. We have minus 4 times 1. And we have 1 cubed is 1 again. And we have minus 4. And for the output here, we have 1 minus 4. And this will be at negative 3. Okay, now in what we have looking at items in the mix, okay, we have yet another composition where we have G composed with f of 5. And in this one case, so for G composed with f of 5, okay, so you already have the compositional notation laid out, okay, and this is going to translate to G of f of 5. Okay, I believe this is the radical I'm thinking of. Okay, now for the output, this is going to be in line with g of x And g of x is equal to the square root of 2x. But now with f of 5 in lieu of x, we have g of f of 5. At the moment, we have the square root of 2 times f of 5. And looking at finding out numerically, okay, what f of 5 will be. Okay, and again, utilizing f of x is equal to x cubed minus 4x. And we have for f of 5, so we have 5 to the third minus 4 times 5. We have 5 cubed is 125. Negative 4 times 5, that minus 20. And for the difference, 125 minus 20, that comes out to 105. And so for what we have for g of f of 5, so we got the square root of 2 times f of 5. We have 2 times 105. And we'll end up at the square root of 210. Okay, and believe it or not, okay, 210, a large even value with 3 digits, much larger than 30. And surprisingly, the square root of 210, okay, that is already in reduced radical terms, because any perfect square above 4 will not go perfectly into 210, and the square root of 210, that is already in exact reduced radical terms. And so for g composed with f, whenever x is 5, okay, the output we have at the square root of 210. All right, now where we have in the crossover to looking at the domain of compositions. And we'll do a little compare and contrast, okay, how we arrive at the domain for the compositions, and how that approach compares with what we have for the domains of the earlier operations with the sum, difference, product, and quotient functions. But for the composition of functions, okay, so you have the domain of the composition of functions will be formed by combining the restrictions Okay, will be formed by combining the restrictions of the input function and the output. with the output being the composition itself. Okay, I'll give you give you a couple of cases here. Okay, so if I were to determine say have f composed with g of x and its domain and we'll say we have given, and we'll say we have, first of all, okay, we'll say we have f of x is equal to, let's say we have x plus 2 and we'll say we have g of x is equal to, and we'll say we have the reciprocal of x plus 3. All right, so if we're looking at f composed with g of x, okay, so we have in this particular case, right, so we have f composed with g of x so looking at f of g of x, okay. Okay, so the output function is going to be in line with f, where f of the input is equal to the input plus 2. So if I follow through, so the input is going to be g of x and if I specify, okay, so you have for g of x, okay, so you have 1 over x plus 3. Followed by the addition of 2. And if I look at combining the expressions, okay, so if I make 2 as a fraction, okay, so you got the least common denominator, okay, it's going to be at x plus 3. Same thing here, 2 is like 2 over 1. Okay, so you got 1 over x plus 3, and multiplying 2 by 1 in the form of x plus 3 over itself. So I'm going to have both of these denominators to be at 1x plus 3. So looking at combining the numerators, so you have 1 plus 2 times the quantity of x plus 3. Okay, so you have 1 plus 2x plus 6 over x plus 3. And we have for the final output, okay, so we have 2x, 1 and 6 will make 7. So we have 2x plus 7 all over x plus 3. Okay, now for what we have regarding the domain, okay, so we're looking at combining the restrictions of the input function as well as the output itself. Okay, so we got the output, the composition, 2x plus 7 all over x plus 3. Okay, now we got the input. At g of x. Okay, so g of x I have equal to 1 over x plus 3. Okay, and in terms of restrictions, okay, now we got a fraction, and so we have that the denominator cannot be 0 in value. So we have that x cannot be negative 3. Okay, now for the output. Okay, so that's just going to be the composition itself. And we had the same bit of history to repeat because here we have a fraction and the restriction is that x plus 3 cannot be 0. Okay, so that means that the only restriction between the input and the output, okay, the input and the output have, okay, they shared the same restriction. And this will be that x cannot be negative 3. Okay. And again, just looking at the domain of the composition, again, we have negative 3 excluded. So you have a whole at negative 3. And we have continuous activity to both the left and the right. So we have in the case of the domain. Okay, so we have at the lower ends, we have those values of x less than negative 3. And we have at the upper end, for the ray going to the right, okay, we have referencing those values of x greater than minus 3. Now let's say that we have a case and we'll say that we have for a given set here. Okay, so if we have f of x is equal to the square root of x, and we'll say we have g of x is equal to x minus 4. So looking for the composition, upon we have f composed with g of x okay, so you have f of g of x. Okay, and so we have the output again in line with f of x. So this time we have f the input is equal to the square root of the input. Now we got the input as the square root of g of x. And specifying g of x, it turns out that this composition will result in the square root of x minus 4. And that's going to be the output. Okay, and looking for the domain. Again, so you have the input at g of x is equal to x minus 4. Notice we don't have an even root radical, nor do we have a fraction. Okay, that can create a zero denominator. Okay, so the terms are, or the whole expression is direct. So the input, okay, there's no restriction. Okay, now for the output itself, okay, so you have is equal to the square root of x minus 4. Okay, so you have an even root radical. Okay, and so with this output, okay, now we have the x minus 4, since we're looking at exclusively working with the real number system. Okay, so we cannot have x minus 4 to be negative. And just putting this in inequality terms. So we have x minus 4 can be greater than or equal to 0. And from this, the defining inequality is going to be that x is greater than or equal to 4. Okay. And so then we'll have the only restriction comes from the output. Okay, because input has no restriction, but the output, so we have the x is greater than or equal to 4. And again, just visualizing. So you have 4. And x is greater than or equal to 4, so you have a solid point thanks to the equal sign. Then we have a ray that's going to go out to the right. And for the domain of this composition, okay, so I'm going from and including 4. So in the interval notation. Okay, 4 is going to be in the brackets. And we have going continuously on out to infinity. And for what we have in the next portion, okay, and we have concerning, okay, what we have with finding out the composition and the domain, and we have for this given set of functions, okay, we have m of x as a radical function, and we have n of x as a linear function, p of x as a quadratic function, and we have q of x as, again, the reciprocal of x minus 10, and we have r of x. Okay, we have the absolute value of 2x plus 3. Okay, so you got a radical, a linear, quadratic, a rational, and an absolute value function. Now, for what we have in the case of number 65, okay, so if I'm looking at this composition where I have n composed with p of x, and I'm looking at trying to find out what the domain is. Okay, so for n composed with p of x, okay, so I have n of p of x. Okay, so the output is going to be in line with n, where n of the input is equal to the input minus 5. Okay, so for n of p of x, so we have p of x minus 5, and p of x I have with x squared minus 9x. Going to have minus 5, and there are no like terms to combine, so we have for the output, as I take out the parentheses, okay, we come out to x squared minus 9x minus 5. And looking for any restrictions, and thus looking at what is going to be the domain. Okay, so you got your input. Okay, so input, you have a p of x, which again is going to be x squared minus 9x. Now we don't have an even root radical, nor do we have a fraction, so I have no restrictions. And again, we have for the output, or the composition itself. Okay, so you have essentially the input once again, except for the minus 5 that follows. So you have no restrictions. Okay, so between the input and the output, so you have no restrictions at all. Okay, so if you don't have any combined restrictions, it's going to turn out that the domain is going to end up being the set of all real numbers. Okay, now for what we have in the case of the next item, okay, so we're looking at P composed with n of x. Okay, and looking at the composition, okay, so you have P of n of x again, you had the output along the lines P of x, whereupon P of the input is equal to the square of the input minus 9 times the input. Okay, and still in variable terms. Okay, now the input, we're going from x to n of x. Okay, so you got the square of n of x minus 9 times n of x. So with n of x at x minus 5, so you have the square of x minus 5 minus 9 times the quantity of x minus 5. And for what we have in the follow through, so for x minus 5 squared, again we have x minus 5 times itself. So again we're looking at x squared minus 10x. You can just do it gradually. X squared minus 5x plus 25, and negative 9 over the quantity of x minus 5, so this will be negative 9x. Plus 45. Now we have just combining like terms together. So you have x squared, negative 5x minus 5x, again is negative 10x. Take away 9x, so we have negative 19x. And we have 25 and 45 will make 70. And that'll be the resulting output. Okay, so for what we have, again, just for the input and the output. Okay, so the input is equal to n of x, okay, which we have at x minus 5. And we have just a linear function. Again, no radical, no fraction. So this part has no restrictions. And for the output, again, the composition, we have all the terms to be direct, and we have no even root radical. So you have no restrictions. So between the input and the output, okay, there are no restrictions at all once again. And once again, we have the domain to be the set of all real numbers. Now, for what we have in the case of m composed with n of x, okay, so we have m of x, we have the square root of x plus 8, and again we have it with x minus 5. So for m composed with n of x, okay, so the output is in line with m, where m of the input is equal to the square root of the input plus 8. Okay, now with the input at n of x, okay, so you have conceptually, okay, we have the square root of n of x plus 8. Okay, now n of x, again, we have with x minus 5. Now looking at following through, so taking out the parentheses, you got x and negative 5 plus 8. So this will come out to x plus 3. And this is going to be the final output. Okay, so and for what we have regarding the domain, okay, so we're looking at combining the inputs and the output restrictions. Okay, so n of x, the input, okay, n of x is x minus 5. Again, you have no radical, no fraction. Okay, so you have no restrictions. Okay, and again for the output, okay, we have the square root of x plus 3. Okay, so we got an even root radical expression. Say the square root of x plus 3. Again, x plus 3 cannot be negative. But again, x plus 3 can be 0 or positive. So we have x plus 3 is greater than or equal to 0. And so we have that x is going to be greater than or equal to negative 3. And so we have for the only restriction, okay, that's going to be with x is greater than or equal to negative 3. Once again, the graphing is optional, but again, just to provide a visual layout. Okay, so negative 3 is the lower limit, and it is included. All the other values will be greater than. So you have in the illustration, okay, we're going to have an array that's going to proceed to the right. And so we have for the domain, so we're going from and including -3. And we have going continuously all the way out to infinity. Okay, now in the case of the next composition, okay, for n composed with m of x, okay, so you have n of m of x, and again we have with m of x, you got your radical expression, but again operating along the lines of n of x. Okay, so you have the output. Okay, so you have a switch around. Okay, reversing the order from m composed with n to n composed with m. So again, we have n of x is equal to x minus 5. And with the input at m of x, you have n of m of x is going to be equal to m of x minus 5. And specifying, okay, so m of x is going to be the square root of x plus 8. And we have followed by the subtraction of 5. And I cannot directly combine these terms together. So for the output, you're looking at the square root of x plus 8 minus 5. Okay, and so looking for the domain. So the input is equal to m of x is equal to the square root of x plus 8. And again, x plus 8 cannot be negative. But it can be 0 or positive. And so we have that x is greater than or equal to -8. All right. And for the output, again, we have the composition itself. So we have the square root of x plus 8 followed by the subtraction of 5. And the only restriction will come from the square root of x plus 8. Okay, so we have essentially the history regarding the input is going to apply for what we have regarding the output. Okay, so in this case, right, for this composition, okay, have the only restriction is that x is greater than or equal to -8. Okay. So again, we have for x is greater than or equal to -8. So -8 is going to be the included lower limit. Everything else will be greater than. So we have a ray that's going to go out to the right. We have going toward infinity. And so we have with the domain. Okay, so -8 is included, and that's going to be bracketed. We have going all the way out toward infinity. Okay, now for what we have in the case of number 70, okay, so this would be our first entry of the function q. Okay, so you have q of x is equal to 1 over x minus 10. And for q composed with p of x, okay, so you have q of p of x. Now again, the output we have in line with q of x. And again, q of the input, again, it's going to be 1 over the input minus 10. So for what we have for q of p of x, so we can get 1 over p of x minus 10. And see, and we have for p of x, see, that was x squared minus 9x. And followed by the subtraction of 10. And so for the output, okay, so we have 1 over x squared minus 9x minus 10. All right. And just looking for the domain. Okay, so we have, once again, for the input, yeah, p of x. And we have is equal to x squared minus 9x. Okay, so for p of x alone, okay, there is no restriction. Okay, now in the case of the output, okay, we have the composition itself, whereby we have 1 over x squared minus 9x minus 10. Okay, and okay, so in this particular case with a fraction, again, the denominator cannot be 0. And if that expression cannot be 0, neither can the factors. Okay, so for this trinomial, we got these factors. Okay, and with the factors of x plus 1 and x minus 10, neither of which can be 0. So looking at the restricted values, okay, so if x plus 1 cannot be 0, we have the x cannot be negative 1. And for x minus 10, if that cannot be 0, we have the x cannot be equal to 10. So looking at the input and the output, okay, nothing restricted from the input, but for the output, we have negative 1 and 10 excluded. Okay, so you got two specified values left out with -1 and 10. And from the graphing perspective, in case you have circles or parentheses, just to symbolize the void of -1 and 10. And everything else will be in the domain. And for what we have in the case of the domain, okay, so we have between -infinity and -1, but not including -1. And for the middle section, okay, we have between but not including -1 and 10. And for what we have at the upper end, we have those values of x greater than 10. And again, so we have in the interval notation, okay, we got two exclusions, okay, which lead up to three subinterval portions. Now, for 76, now this one is seemingly reflexive. Now we have composition between a function and itself, where we have p composed with itself of x. And in this one case, you have what's going to be p of x. And again, just for p of x, you have x squared minus 9x. Okay, now for p composed with itself of x, now you're operating along the lines of p of x, but instead of the input at x, you have p of x. So you have a bit of a clustering that's involved. Okay, so you're already working with p in terms of the output, and the input we already have at p of x. So again, you're sort of doing a bit of amalgamating. So you have the square of p of x minus 9 times p of x, and then just specifying. Okay, so for the square of p of x, we're taking the square of what, and that's going to be the square of x squared minus 9x. We have minus 9 times p of x, so we have minus 9 times all of x squared minus 9x. And just gathering what we have now. Okay, so we got the square of x squared minus 9x. So if you envision, say, x squared minus 9x times itself, so you have x to the fourth, and you have minus, outside product would be negative 9x cubed, inside product also negative 9x cubed, and negative 9x times itself, that's going to be plus 81 x squared. And then for the other distribution, so you have negative 9 x squared, and negative 9 over negative 9x, so that's going to be a positive 81x. And combining like terms together, okay, so you have x to the fourth, and we combine the cubic terms, so we have minus 18x cubed, 81x squared minus 9x squared, so that'll be 72x squared. And we have plus 81x. And we'll scan for what we have in the case of the input. Okay, so the input at p of x equal to x squared minus 9x squared. And we have no restrictions. And again, we have with the output, again, we have this fourth degree expression. Again, since I don't have any even root radical or fraction, okay, we don't have restrictions for the output. Okay. All right, so you have no restrictions at all. And so we'll end up with the domain being the set of all real numbers. Okay, and just kind of looking at what we have regarding domain. And we'll say we have here given. Let's say we have f of x and we'll say we have in this one case, so we have f of x is equal to the square root of x plus 7 and we'll say that we have g of x is equal to x plus 2 if I were to determine the domain of the following. Okay, so first of all, okay, for the first item, and so for f of x is equal to the square root of x plus 7. Okay, now for f of x is equal to the square root of x plus 7, again, x plus 7 cannot be negative. Okay, and so we have x plus 7 is greater than or equal to 0. And so we have that x is greater than or equal to negative 7. And so we have for the domain, for x is greater than or equal to negative 7. So we're going from negative 7 and including negative 7 all the way out to infinity. Now for g of x is equal to x plus 2, for g of x is equal to x plus 2. Now that one has no restrictions. So for g of x, if I had to worry about just g of x, okay, so for g of x, x can be anything since I do not have an even root radical or a fraction. So the domain is going to be the set of all real numbers. Okay. All right. Okay. Now again, for the sum, difference, and product functions, now these are going to have the same domain. So let me just kind of go back. So you have f of x equal to the square root of x plus 7. Again, the restriction is that x is greater than or equal to negative 7. And for g of x equal to x plus 2, again, no restrictions. All right. And again, we have with the sum, the difference, and the product functions. Now, those will have the same domain. And between f of x and g of x, now for the sum, difference, and product functions, we're combining the restrictions from f of x and g of x. Now there's no restriction on g of x. Okay, so I can plug in anything for x for the g part for the sum, difference, and product functions. But I still had to be able to work with f of x so that x is greater than or equal to negative 7 is the only restriction between the functions, and that is going to be carried over to the sum, difference, and product functions. So the domain of the sum, difference, and product functions will be the same as what we have for just f of x. Okay, so the sum difference in product functions will have the same restrictions, thus the same domain. And again, we have for the quotient function, this can be potentially with a domain that's different from the other three prior operations. So in the case of f over g of x, so just laying the groundwork here. So you have for f over g of x, so again we have f of x over g of x. Okay, now again for f of x we have the square root of x plus 7. And for g of x, again, we have x plus 2. Okay, now again, we have a twofold situation. Now we have a radical term with the square root of x plus 7. And now g of x and the sum difference product and just the standalone g of x itself, there was no restriction. Now there is, since g of x is situated at the bottom. Okay, so we have with the square root of x plus 7. Again, you got your radical. Again, so you had that x must be greater than or equal to negative 7. And at the same token, for x plus 2, x plus 2 cannot be 0. So we have that x cannot be equal to negative 2. All right. So looking at what we have for the quotient function. Now, we're going to have still part of x is greater than or equal to negative 7 to be applied. But also you're going to have negative 2 excluded. So again, we have to keep f of x happy. X has to be greater than or equal to negative 7. And for the avoidance of allowing g of x equal to 0, again, x cannot be negative 2. So in terms of what is going to be the domain of the quotient function, and this is where graphing can definitely be a helpful tool. Again, for the values of interest. Okay, so you have x is greater than or equal to negative 7. And you'll start to go out to the right. But notice there's going to be a roadblock since x cannot be at negative 2. So everything from and including negative 7 approaching but not including negative 2 will be in the domain, and once you bypass 2, okay, the coast is going to be clear in terms of the follow through. And so for f over g of x, what's going to happen here? So we're going from and including negative 7. And then we have approaching but not including negative 2. So you have a parenthesis. And then for the rest of the domain of the quotient function, again, we have those values of x which will be greater than negative 2. Okay, so for the sum difference product functions, you're looking at combining the restrictions from f of x and g of x. Again, for the quotient function, you're kind of doing the same thing, but avoiding the denominator in the quotient from becoming 0. Okay, now again, just partially hitting the reset button, and just regarding the composition. Now if I'm looking at the domain of f composed with g of x, okay, so I'll be looking at both the input as well as the output, which will be the composition itself. And for f composed with g of x, so I have f of g of x again, we have the output, okay, we have at f, and again, f of the input is defined by the square root of the input plus 7, okay, and with the input at g of x, okay, so I have the square root of g of x plus 7, and g of x, again, we have at x plus 2. So we have the square root of the quantity of x plus 2 plus 7. And combining the constants, okay, we have the square root of x plus 9. Okay, and so what's going to be entailed, okay, in terms of the domain of that particular composition, okay, so we have the input at g of x, which is equal to x plus 2 and just g of x. Okay, again, we have no restrictions. Now for the output, notice before we had the square root of x plus 9, and notice from the prior operations there was no 9 involved in any capacity. Okay, just from the prior operations we were dealing with like the involvement of 7 and the additive inverse, negative 7. Okay, but now for the output, okay, now we have x plus 9 to come along. And this time around, so we have with the square root we have the x plus 9 cannot be negative. And it can be 0 or positive. So you have x plus 9 is greater than or equal to 0. And so you have the x is greater than or equal to negative 9. Again, between the input and the output, the only restriction is that x is greater than or equal to negative 9. Okay, so you have from and including negative 9 And the rest of the values, okay, have to be greater than. So I have a ray that's going to go out to the right. And we have approaching infinity. Okay, so for the composition, whereupon we have f composed with g of x it's going to turn out that for the domain, okay, so we're going from and including -9. Okay, so that's going to be in the brackets, and the rest of the values we have going out toward negative, or I should say going out to positive infinity. Okay, so we have for the domain, so you have from and including -9, and we have going out to infinity.